Welcome to Drone System and Control course. Okay. In the previous lecture, we talked about autopilot architecture, autopilot design, and then flight control architecture. We talked about yaw subsystem, we talked about vertical control and horizontal control. Finally, we show the complete realization of in MATLAB. Now we are going to do a demonstration of the entire implementation and take you through. Okay. This is a quadcopter control. Okay. Basically, what happened is these are our whole system. If you see it, right? You have a airframe, that's the dynamics, and then you have a sensors implemented that gets a state variable that goes into my control loop. I get the propellers and whatever information required, I send it to the motor, right? Because of that, I get the necessary force and torque. Okay. Now, if you look at a simple control system architecture, we talked about this, the plant dynamics and then controller dynamics, right? And the command input which goes in, and that's the output state, and the output state takes in as an input, right? Now, we talked about it's better to implement a PID, the control structure, right? The command comes in, the state variable comes in, that's error. The error I am passing through proportional gain. I have the integral system, I have the derivative, the output is my controller output, which is basically U, which goes as an input to my plant, right? So, if I am trying to realize them in equation form in time domain, the control input U depends on proportional gain, integral gain Ki and derivative gain Kd, right? And depends on the error which goes as an input to the control system, right. Now, let us look at a PID basically to control the Z motion of the quadcopter, right. Basically, we are looking at a vertical control system. I am going to demonstrate only for a vertical control system, right. So, what we are talking of, I want to increase my altitude or decrease my altitude. So, increasing my altitude means my altitude is negative, right, going above is negative, Z is negative in the above the mean sea level, Z is positive below the mean sea level. You just have to understand the body frame of reference that what we are talking of, right. Now, what we want, I am taking this dynamics, and when I see the response of the drone for thrust, I am just commanding. If I just give a thrust input, my velocity is initially 0 and velocity keep increasing when I keep increasing the stick, right. And you see the position of the drone, Z position, it started going in exponential sense, right. If the force is 0, the quadcopter falls, right, and results of that, right. So, now I can control what will be my F, right. I can control this and see my different responses, right. Now, I want a simple proportional controller, MKP is desired minus this proportional controller. Suppose if I implement a simple proportional controller, you see the position and this, it is neutrally stable, it start oscillating, it is not sufficient. So, I need my derivative controller also into picture, so that I can control the responses of the system, right. So, I am bringing in my small derivative control system, proportional and derivative. You see what happens when I give an input, the velocity initially increases, then the velocity comes to 0. Because velocity comes to 0, my drone initially start climbing. Once it reaches the 10 meter altitude, it remains stationary there. The PD controller helps me to achieve my desired height, right. So, I can do that. Now, if I want to increase and add an integral, there is a bias, there is a small difference is there. I do not want that difference, I want exact 10 meters. It is not exactly 10 meters, if you see it is somewhere around 9.9 or 9.8 meters it will come. I want an exact 10 meters, the steady state error present here I want a 0, then I have to add the integral component to it. If I do an integral component to it, then I have, right, the proportional integral. You see now what's happening. My velocity comes back and 0, but you see the position, right? It goes to minus 13 and start oscillating. Now what is our control requirement if you remember? I want a 0 overshoot. So what do? Can I play with these gains, right? If I keep increasing the gain, right, or I can vary the proportional integral gains and see how the system responds, right. So if I vary the gain, I can change their response characteristics, right. So how do we do that? What we do is we take a open loop response for a step input. So we can use a reaction curve method, right, or we can find out what is a critical gain. From critical gain we can find out what should be integral and derivative values. Based on those values as a nominal value, we can add and we can go into the simulation and see what value of Kp, Ki, Kd I achieve what is my desired performances, right. I can change the gains, right, and check what's happening. You see, by increasing my gains, I started reducing my overshoot, right. I can decrease my derivative gains. You see oscillations start coming up. If I increasing my derivative gains, my oscillation decreases, right, and I start getting my response more and more lesser overshoot, right. I can increase my integral gain to get my steady state error, right. So every time you change, the response characteristics changes and then you can fine tune it. So either you can do get a guess based on the linear approximation. We can find out what is a Kp, Ki, Kd, but once you have the Kp, Ki, Kd, those are nominal values. You substitute them and you tune the gains in a way what you wanted to reduce. I showed you here in a previous response, it start oscillating. You see its overshoot is there, close to 4 meters of overshoot. I don't want overshoot. I don't want quadcopter to oscillate. So I can control the gains accordingly and get my response. Once you have the Kp, Ki, Kd values, tuned gains, you can implement them and verify the response, right. So this you can get an intuitive understanding of how these gains influence, right, how they interact among each other so that you get a proper response. Now you can also look at feed forward controller. Instead of putting it, I just want to put a feed forward controller and see how it is responding to it. Okay, if I just see it, there is a feed forward controller, then there is a PD controller combined, and that's my output which I am just passing into the system, right. Now you see this is the response we are getting by adding a feed forward controller, right. I can change the gain, right. I can change my Kp. More and more I change, you see the response become faster and faster. If I reduce my Kp, response becomes slower and slower. It takes some 9 seconds, 10 seconds, still is not reached the desired value. If I increase my proportional gain, response become faster and faster, right. At the gain, so now you see my response is almost in 2 seconds I am able to achieve the desired altitude. If I want to reduce my oscillation, I can increase my gain. So Kd will reduce oscillation but also influence. If Kd becomes smaller, I see an oscillation. If I adjust my Kd, right, you see there is no oscillation now. So you can change your proportional gain affects the response time. Kd becomes smaller, you start getting oscillation, right. And if too high Kd, sensor noise will come into picture and that becomes a response to the sensor noise. You may consume more power, right. So we can just tweak the gains based on the requirements, specification requirements, and then that gain we can implement in our system. See, currently I am just demonstrating everything with respect to 10 meter, right. I have a forward gain and I have PD implementation. Now let us look at how do we do it for attitude control system, right. I am assuming that there is a mixer exists, right. That mixer takes care of the desired attitude to RPM. We talked about in the previous lecture. If it's a quadcopter, you have the matrix which is invertible, and you can invert the matrix based on U1, U2, U3, U4. You can get omega 1, omega 2, omega 3, omega 4, right. So, I have that already in picture, right. So, what I am looking at? I am looking at a PD control for pitch, roll and yaw, basically along with feed forward plus PD control, what we did similar to thrust command, and then I have a motor mixing matrix, and I am just going to see how it is going to work, right. We talked about building of a basic quadcopter in the previous lecture when we talked about module 2, talking about rigid body, and then we talked about the dynamics of it. We demonstrated how this can be implemented in Simulink, so I am not going over again. So, I have the entire dynamics available to me. So, I take the quadcopter model, I am going to create the mixing matrix, I am going to get my feed forward control and PID for the thrust, I am going to create yaw and pitch, and I get this whole thing, right. So, what I have done here is I have shown you individual subsystem, how you can tune your gains, right. For example, here if you see, here I showed you by putting a forward control gain and a PD gain, how you can tweak the response, what is the best response that you want to have. If you see here, it takes almost 3 seconds to settle. If you want to change faster, you can increase the gain, right, and see how quickly it responds. So, okay, 1 second it reaches from steady state initial point to a final point, that is fine with me, and I am okay with that. Then this is the gain I am going to take. With this gain, what we are going to do is, okay, so I am going to take the entire dynamics. Let me see how I zoom in bigger. Okay, so I have implemented the dynamics. Okay, this is my dynamics. I showed you in the previous lecture. This is my display. This is my body axis. I am taking a force and moment, and I can translate this Euler angles, and I can get my velocity, position, right, my rates, my attitudes, right, all that information I can get. I have the drag force and gravity model, right, implemented, and that will just give me the drag force and gravity. Then I have a UAV dynamics which takes care of the propeller speed as an input, and it computes what is the force and torque. This basically I can do a thrust bench where I connect the motor and a specific propeller for a specific RPM, what is my force that I will get, what is the torque I will get, I have that relationship. Then I have a motor control system which basically takes the thrust, roll, pitch, yaw as an input, and then you have the mixing matrix. If you want, I can just take you and show you. This is my feed forward path, this is my mixing matrix, these are U1, U2, U3, U4. I'm mixing it, and the mixing matrix is multiply, you get your what is the RPM required, and you have a forward path, forward control combined together, you gives this output. When you sum them, you will get the whatever the output needed. I am just trying to see whether there is a saturation is there or not. If not, I am just sending it out, and that is my propeller speed, right. The propeller speed is used for me to get back to this relationship, right. If you look at this, again I am taking a propeller speed, I am passing through a speed limiter, basically looking at what is the limits on the speed, whether the propeller can run at this particular speed or not. Then I am looking at the angular velocity square, omega square, we know that it is square of thrust and moment produced from the propeller, square of the angular velocity. Then I get the thrust in all four, and looking at the propeller geometry, right, I have implemented and get my momentum and and the torque which I can get, and convert everything into body coordinate system. This will be in a motor position, right, it is sort of specific. I have to do the transformation to body coordinate system. That body coordinate transformation also is there, and I get my moment as well as force in that particular coordinate system, right. Then I pass on this Then comes the environment. We have aerodynamic drag, we have the gravitational force, and I compute based on the states of the system, I compute the drag force and gravitational force, and that also passed on to your final Euler body angle system. If you look at Euler, you can define how you want this system to be, transformation to be. You define all this based on the coordinate representation system. It transforms the forces and you get the net forces, and then you can run the x dot is equal to f of xu is what you saw, it's implemented here. You have a census, so I'll take you to the attitude control system. You'll understand how it's been realized. This is your altitude control system, is basically a vertical controller, right? So you have the error coming from the reference, you have a ZD, and these two passed on to PD control, and that will give me my thrust, right? If you look at attitude, that is basically a horizontal control, roll desired, pitch desired, yaw desired is sent, and this is coming from my Kalman filter, estimated value. I am passing on to PD control for roll, pitch also PD control, yaw also PD control. That will give me a roll rate, pitch rate, and yaw rate requirement, right? So I can pass this to rate control system. If you look at a XY command, this is a position control system, right? I take X demand and Y demand, passing on to conversion into change in X, change in Y, and pass this change in X, change in Y to get the RD and PD, and that's error, RD and PD error. I'm just passing on to PD control system to get my roll and pitch. Okay. So if you see, I have implemented the whole loop. What's my command here? The drone should take off and go to desired altitude. You see, this block defines what is my altitude I want, right? Think about it in a microcontroller architecture. It could be a RC stick can be directly connected here. The stick can just give me a height what I am looking for, right? What is my desired X position? I am looking at 10 meter. Y position is 5 meter. Yaw command is 0. I don't want the aircraft to yaw. Based on the previous MLX file where I showed how to use the PD values, feed forward gains, we do that, choose the respective PD value, we implement it in the attitude control, position control, and altitude control, and then we can run, right? Now I want the aircraft to go to 10 meter and stay. I can check the responses. You see here, this is my response figure. Okay, I am trying to get my desired velocity. See a velocity command, right? And it goes back to 0. There is no u velocity, there is no v velocity, all of them are 0, right? I go to a 10 meter in x plane, I am just holding there, and 5 meter in y. Then you have z is minus 10, which basically you go to 10 meter altitude, you hold your altitude. And these are your rates, how your pitch roll, yaw rate is 0, I am getting a desired yaw rate, and my pitch rate depends on the command that I am giving. Pitch rate and roll rate comes into picture, right? Attitude and roll. So this is very important to see the XYZ, right? I reached my desired X, desired Y, desired Z, right? And my velocities are 0 once I go to equilibrium point. This is a requirement. So I can now, if I am not happy with the speed of response, or if I am not happy the velocity change is going so much in vertical plane, I want to reduce it, I can go back and change my PD gains appropriately so that response time will vary and substitute back again, and I can verify with respect to full nonlinear system. Whenever we design a controller, we take an equilibrium point and linearize it, and we just do it. When we do linearize, we approximate this system, right? Nonlinearity. That approximation do affect some time. So what we do is we just get the PD values, substitute in this, and then simulate and verify. Okay. So that way what I can do is I can understand how I can how to fix these gains and how to give the desired value and get this response as desired by the user, right. Basically 0 overshoot or steady state error to be 0. We can check everything and then substitute it and look at all the control inputs, whether it is saturating or not. All that can be verified nicely in the implementation. So what happens is in the we are now looking at how do we tune the PID, right? How this PID is going to be and what are the how we can just get it, some exercises, right? So here PID tuning, see command is coming and you have the controller, you have the plant, you have the output. You need to understand how this proportional gain influence the control output, how the integral gain influence output, how the derivative gain influence output, right. The proportional will just help you to go to decide as quick as possible, whereas the derivative will prevent your overshoot or the oscillation, right. Integral term basically necessary to make sure that steady state error is 0, right. So you have these three, but they are interactive. If you increase the KD, if you increase the KP, that will also have a effect together. So what you need to see is when you run this system, when you see the output, and you have to look at is that desired, which basically you need to understand. If the pilot says I want a height to be increased by 10 meter, if the aircraft takes 10 seconds to reach that 10 meter, you consume more energy. If you say your aircraft want to go to 10 meter instantaneously, then what will happen is acceleration will be very high, right. So you need to understand the conversion of the demand to the response characteristics, right. If you want to go to the position, let us say XY position 0, 0 to 10, 10, the time it has take to reach that position is very important. If the time is too small, it will pitch very fast to get the higher velocity. If it is pitched very fast, then it will tilt more and the aircraft may not be stable, right. So you need to convert the demand to desired value. That is very important. That is where you need to play these gains and to understand how fast you wanted to respond. For example, if your objective is to hover it at 5 meter, okay, then your state error will be like 5 minus Z of t. That is your proportional error, right. So what we are looking at, I am looking at this is a KD is 0, Ki is 0, and I am just taking the whole mass of the aircraft is 1 kilogram, right. I am trying to see what will be my response. You see the Z response is so much oscillation is there, right. I do not want my oscillation, I do not want my aircraft to go at 5 meter and keep jumping up and down like this, and it takes its own time. It is much more than 30 seconds is still not settled at 5 meters, right. So I do not want that to happen. So what I need, proportional controller alone is not sufficient, right. I need to add. What is that I need to add? I see a oscillation. I wanted to decrease the oscillation. So if you see, I want to bring in the PD controller into picture. The proportional alone, it gives me a problem. If I am superimposing the velocity on a proportional, you see how my velocity is changing, right. A small variations, but it sees the oscillation comes into picture. Now if I am going to bring in PD controller, D controller is specifically for reducing the oscillation, right. So if I bring in the PD controller, I kept some values of proportional, I kept this, there is no integral gain being there, right. If I just putting a just PD controller, you see it is nicely going up and settle, but the time it takes is less than 1.5 second. It accelerates very fast to go to the desired altitude, but if you see there is a steady state error. I want 5 meter, but it is reaching only about 4.7 meters, still not reached the 5 meter, right. So that steady state error is a concern for me. The final altitude is only minus 4.7. It's reaching only 4.7. I want the final altitude to be 5 meters. So PD alone is not sufficient. Then I need to bring in a derivative controller because I want that to be there. I put a proportional controller, derivative controller and integral controller. I put the P gain, D gain and integral gain. You can play the gains and check what happens. Now what happens? If you see my response, right? So what we did is we have to do the PID control. Moment you put proportional, integral and derivative, you see it nicely goes up and settles at this value. But you can change the gain. If you increase or decrease the gain, it's a rate at which, if I change my proportional gain, right, it just changed the way my response characteristics is going to be. So I can tune my proportional, integral, derivative gains and get a proper response characteristics based on the acceleration that is acceptable to me, response time that is acceptable to me, and I can find those gains here. And using that gain, I can just go and play. Right now, you see here what I was telling. When I am talking about, it takes almost 1 second to reach the 5 meter altitude, close to 1.1 second or something, right? But it start going higher and higher. If you want the aircraft nicely go to 5 meter and stays there, then you need to adjust your gains appropriately so that you don't even have a overshoot. Yes, a small overshoot is there, 5.1 meters it comes to, right? I don't want that overshoot. So I can control this, right? So we can just look into how we go and tweak these gains and depends on the requirement and control there. In attitude block, we have a PID, right? For 3 PID controls are there for roll, pitch and yaw, and 2 PID controls are there for X and Y. Totally you have a 6 PID controllers are there. You can fine tune each and every one of them based on the response that what you are looking at, right? Remember, not all states are independent from one another in a quadcopter, right? You cannot hover in one place in windless environment unless you roll and pitch and angles are 0, right? Likewise, you have to initiate. So you have to understand how these states of the systems are combined. You need to fine tune your PID, right? And based on this, right? So you can try. We'll be sharing the Simulink files, right? You can try Simulink, tune the PID to altitude to desired response. For example, I can open the model, right? I can look at the realization, right? I can look at the altitude control. I can change my PD gains. Right? I have kept a proportional gain and derivative gain. I can change them the way I want such that the response characteristics can be controlled. Right? So suppose if I say auto tune mechanism, right? The whole system linearize, it goes into auto tuning, right? You get the response, okay? So it just tunes such that the response are based on the requirement, and I can say that's what I want, I'm okay with that, apply to this. Okay. So based on this, you can run the simulation again, right? So I'll just show you and how the PID tuner looks like, right? In the PID tuner, I can play with how fast my response going to be, right? How slow the response going to be, right? So this is the response that you get for pilot input to go for 1 meter altitude variations. Okay. You see the response time is too fast, you can reduce the response. Okay, so it becomes this much time it takes to reach, right? You can make it slower. If you see the acceleration is too high, you can reduce it. And if you see that you want it to be very aggressive, which means you can accept overshoot, right? Then the response will become aggressive. So this slider, it talks about what is that user expecting. You, for a given pilot input, how your response, how the system response should be, right? You want a system to respond slow, you want a system to respond faster, you want the transient behavior to be robust, means I don't want any oscillation, I want to be robust. I can say that this is what I want, right? Then I can just say update the block, right? So what we can do is we model the whole system. Moment you trigger this is linearize the plant. Based on the linear plant, it shows your response characteristics, it shows your response time and transient behavior. You can control the response time, how you want the system to respond. You want to respond slow, you want to respond fast, you want the transient response to be more robust. You can do that, right? And once you do it, you say update. The corresponding PID gains get updated, and that's what will be implemented here, right? If you go back, it gets updated here, right? And then you can just check your responses again, right? So it's a process. Same way you can do it for your roll, pitch and yaw. For every subsystem, you linearize it, you look at the first order, response characteristics, you see how the response is. Usually the pilot will look at how fast for a given command, how fast the drone is reacting. That's very important, right? It's like when you are buying a car, right? What is that expected? Moment you give an accelerator, you want the vehicle to reach the maximum RPM. It takes 10 minutes to reach the maximum RPM, you will not be buying the vehicle, right? The response time is very important, how quickly it responds, right? The second thing is how robust it is, right? Is it oscillatory? Sometime I need aggressive. Someone who is going for a race, he wants aggressive characteristics. Suppose you are carrying a sensitive payload, you want the response to be more robust. I don't want any oscillation or anything, I just want a robust, right? Suppose you are doing an fastest time to reach, right? Gaming drones, they want an aggressive response to it. So you can decide based on the user requirement. You remember in the beginning of the lecture I said the functional aspect of it, how the pilot is expecting the vehicle to respond for a given command, the response time and whether it is aggressive or it is robust, right? So based on that you can slide and it automatically computes the gain, and that gain gets implemented. Once you update, you can run the system and verify. You can even change. I already kept this 10 meter altitude, X position to be 10 meter, Y position to be 5 meter. You can replace this and provide a trajectory. Get me this trajectory, right? And you can see how effective it is in following the trajectory, right? So you can go back and tweak the controller. X response is too aggressive, right? Whereas Y and Z is normal. You can go to X control, right? You open this X control, right? Look at the estimated dx dy and you want to change the PD corresponding to pitch, you change it in the PD control here, right? You modify the PD control. You open the auto tuning mechanism, it will linearize the plant around the condition, it gets a linear response, and you play with this response time versus aggressiveness, modify and accept that gain, and that will be implemented, right? So the architecture is what is very important. Understanding the relationship between proportional and integral derivative you should understand, and once you understand, you can look at the response characteristics and automatically you can tune the gains and implement them, okay. We will be sharing all the Simulink files in our course folder. It will help you to practice, right, understand them, implement them and appreciate how these 6 different PID controllers helps the drone to track the trajectory. Thank you.